Hi, this is Professor Fernandez working on Class Notes B in Lesson 11. In this example, I'm asked to find a basis and the dimension of this space. So this is known as a space of 2 by 2 matrices with real entries. So we want to find a basis for this, right? We want to find a set of 2 by 2 matrices with real entries that are linearly independent and span the space. I'm not given much guidance for how to do that, so I'm going to follow along the footsteps that we did in the previous video. That is to say, I'm going to try to find a basis for the space by first taking a general element of the space and effectively working on the spanning part of the basis argument. I want to take this general element and I want to decompose it into simpler elements of the space. So again, this space happens to be 2 by 2 matrices, all with real entries. So I want to try to decompose a general element into some simpler 2 by 2 matrices with real entries. Seeing this for the first time, what I'm about to write will make sense in hindsight, and then will help you later on if you're going to do something similar with a different space. A simpler element might be, for example, what if I just pick off the A22 element and I make it, I put it into its own matrix, right? Well, you might think that's probably complicating things, but not really, because I have broken up, made simpler this general element, right? And we now have a lot of zeros that have appeared in this second matrix. So this matrix is going to be generally simpler than that one, which could have a bunch of crazy numbers in it. So I'm going to follow in that same footstep, and you can kind of see where this is going to go. I'm going to siphon off the A21, put it in its own matrix, okay, and then leave the one that I had here. And then I'm going to, then also take the A12 and make it an element of its own matrix with a bunch of other zeros. A21, 0, and then 0, 0, 0, A22. Okay, and then one other thing I'm going to do is I'm going to say, oh, but wait, I can get even simpler. The A11 I can put over here, because remember, that is how we defined matrix multiplication. Whatever number this is, multiplied by this matrix, means I just multiply it everywhere into every single element. But these are all 0, so that doesn't change. When I multiply A11 times 1, that's when I get this element. Great, so that's really nice, because I can just do the same thing with the rest of these elements. A12 here, 0, 1, 0, 0. A21 here, 0, 0, 1, 0. And then A22, 0, 0, 0, 1. Okay? So now I'm going to call these matrices E1, capital E, capital E2, capital E3, and then capital E4. I'm choosing to do that because I want you to be remembered, to be reminded of the basis vectors for Rn. So I'm just going to scroll up and remind you what those are. So here they are, right? This is after the previous video. So this is what the basis vectors for Rn, the sort of canonical basis. What we mean by that is the simplest basis you could think of. There are many, many other bases for Rn. But for this example, I want to use this E sort of notation because it feels very much like a similar type of basis just for this matrix space. You have matrices that have a 1 somewhere and 0 everywhere else. And where that 1 is kind of just shifts around. So great. So I have now shown that this is the spanning step, right? I have shown that if I look at a matrix that looks like this, which is in the space of 2 by 2 matrices with real entries, I have shown that it can be written as a linear combination, right? These are all constants of these very special matrices that are also in the space of 2 by 2 matrices, okay? So this calculation shows that E1 through E4 span the set M 2 by 2. So now I'm going to go back and do the linearly independent part. And excuse me, let me pause to just point out that what I've done is very useful because, as we said at the beginning of this video, we had no idea. We're supposed to find a basis, so we have no candidates to look at, right? What matrices are we going to show are linearly independent and span? So starting with the spanning part of that task allows us to develop some guesses, some candidates for the basis. And our guess now is that these four matrices, E1 through E4, are a basis. We've certainly shown that they span, so now let's show that they're linearly independent. So how do I do that? Well, I'm going to follow the usual route. I'm going to go to the definition of linearly independent, form a linear combination of these four matrices, and then set it equal to the zero element in this space. We're talking about 2 by 2 matrices with real entries. So the zero element there is the zero matrix of size 2 by 2. Great. And I'm going to use my properties of matrices here. And rather than write all this out, I'm just going to point because, for this example, it's kind of nice what's going to happen. What's going to happen is we've already done this. So, if you look at this linear combination on the left-hand side, it is the same as this linear combination, except that C11 and A11 are the same thing, right? C2 becomes A12, and C3 becomes that, and C4 becomes that. And this, right, is equal to that, which is equal to that. So we just keep going, which is equal to that, which is equal to that, which is equal to that. Okay, so long story short, this left-hand side literally becomes C1, C2, C3, C4. And again, you can see that pretty right from this expression by excuse me, using the fact that E1 through E4 have a bunch of zeros in them, except for a 1 in this appropriate place. Okay, so we come back to this fact that we're setting it equal to 0, 0, 0, 0. And this tells us that C1 and C2 and C3 and C4 are all 0, right? So this shows linear independence. Up here, this showed span, and therefore they're a basis. So we found a basis. And then the dimension of the space. So, I'll just write it here. So we've shown that E1 through E4 are a basis for the set of 2 by 2 matrices with real entries. The dimension of this set is equal to the number of elements in the basis, right? There are 4 of these, so the dimension is 4. And that's it for this video.